We saw the LU factorization in week 6. We then modified that to become the LU factorization with partial pivoting in week 7. And in the enrichment for week 8, we talked about the Cholesky factorization. What we're going to talk about next is the third important factorization, and it's called the QR factorization. Notice that in the previous 2 units, we learned about the Gram-Schmidt process, and the Gram-Schmidt process computed vectors q0, q1, etc., and scalars rho 0, 0, rho 0, 1, etc., such that the original vectors that you were given were linear combinations of the vectors that were computed, where the coefficients used in the linear combination were given by these scalars, rho sub 0, 1, 1, 1, etc. And that was true for each of the vectors with which you start. Now let's look at this a little differently. If we look at the first vector is just a scalar times the orthonormal vector that was computed from it. And one way we can think about that is as a first column in the matrix times a first element in the matrix, like this. So that relates the first column in a matrix to a multiplication of 2 matrices, one of which is going to be Q and the other one of which is going to be R. Now let's look at the next vector, A1. A1 is a linear combination of the vectors Q0 and Q1. If we place Q0 and Q1 in matrix Q, and we place rho 0, 1 and rho 1, 1 in the next column of our matrix R, and importantly we place a 0 here so that if we do this times that plus this times that, we still end up with this result right here. Then we see how all of these are related. We can continue like that. And if we look at the last vector is a linear combination of the vectors q0 through qn-1. Those become the columns of our matrix Q. These coefficients become the last column of our matrix R. Recall that if you do a matrix times the last column here, you inherently generate the last column there. So those are equal. And you need to place zeros below the diagonal here because this first column should equal q0 times rho 0, 0, and as long as we have zeros here, all of these columns have no effect at all. The second column is computed as q0 times rho 0, 1 plus q1 times rho 1, 1, and then we have zeros for the rest, so the other columns don't affect it. So we get exactly this, and so forth. And what we notice is that we get a matrix that has the vectors q as its columns, multiplying an upper triangular matrix. And that's known as the QR factorization. So now matrix A can be written as a matrix Q times R, and that will always work as long as the columns of A are linearly independent. What we conclude is that the Gram-Schmidt process computes this QR factorization. It's a matter of arranging all of the vectors computed by the Gram-Schmidt process and all of the scalars computed during the Gram-Schmidt process as a matrix and then an upper triangular matrix. This QR factorization turns out to be extremely important, and in the next unit we're going to talk about how the QR factorization can be used to solve the linear least squares problem.